Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking for the first time at what you call the geometric distribution. This is also the first video on the entire channel about any probability distribution. In my opinion, whilst this is not normally the distribution that people start with, they normally start with the Bernoulli distribution or the binomial distribution, I think this is the simplest one and I'm starting with this one. So if you don't know what a probability distribution is, you're also in the right place. But let's just not worry about the name, the geometric distribution. Let's not even worry about what that means. Let me just give you an example of a fairly simple, very easy to visualize situation. Let's play a game where I roll a die until I land on the number 5. Let's write out the probability distribution, which hopefully you're pretty familiar with. Link in the description to my probability playlist where I've got lots of content on this. But let's write out the probability distribution of that. So what I'm talking about here when I say the probability distribution is I'm going to say that I've got a random variable x, and in this case, it represents the number of rows it takes me until I get a 5 on my fair die, okay? On my or a fair die, okay? So just to make sure that makes sense, I'm rolling a normal fair 6-sided die and I'm going to keep doing it until I land on the number 5, and then I'm going to stop playing the game. And x is the number of rolls that it takes up to and including getting that 5 for the first time, okay? Let's just think about this. So it could obviously take me 1 roll, or 2, or 3, or actually arbitrarily many rolls, right? I could just technically land on the number 1 over and over and over and over and over again forever, technically, but that would be very unlikely, of course. But let's just think about this. So our sample space is all of the positive whole numbers because it could take me just 1 roll or 2 or 3 or any number. So I've got a 1, I've got a 2, I've got a 3, I've got a 4, I've got a 5, and that's going to go on forever. And the question is, what is the probability of getting my 5 for the first time in my first go, or in my second toss of the die, or third, or fourth, or fifth, or sixth, etc.? Well, okay, how would I land on a 5 for the first time? What is the probability of that? Well, it's 1 in 6, okay? 1 in 6. So the probability of getting my 5 for the first time in the first roll is just 1 in 6. Hopefully that kind of makes a lot of sense. What about in the second roll? Well, the only way for this to happen is if I roll my die, I do not get a 5, and then I do get a 5 in my second roll. That's the only way that this can happen. So those two things are independent. So we're going to multiply the probabilities of both of them together. So I need to not get a 5, which has a 5 in 6 chance. And then I need to get the 5, which has a 1 in 6 chance. So I've multiplied these together, 5/6 times 1/6. If you want it as one number, that would of course be 5 out of 36. What about 3? In 3 rolls. So that means I'm going to roll the die, not land on 5, roll it again, not land on 5, and then roll it for the third time, and only then do I land on the number 5. What's the probability of that happening? Well, I need to roll it and not get a 5, so that's 5 in 6. Then I need to roll it again and the same thing has to happen. So times by 5 in 6 again. You could also think of this as just squaring that. And then I need to do that 1 in 6 thing of getting the number 5. And maybe you can see the pattern, but let's do one more. For 4, I need to not get a 5 3 times. So 5 in 6 cubed. And then I need to get it. So 1 in 6. Okay, and just for, just for luck, we'll do one more. There we go. And just to be very clear, it doesn't stop at 5, it goes on forever, because it could take me 17 attempts to do this, or it could take me 301 attempts to do it, or whatever other number that you want to think of. It could take that long, but you guys can see that as this goes on, the probability is decreasing every time. It's becoming less and less and less likely. So eventually the probability is going to become arbitrarily close to 0, which means as this list goes on, it becomes less and less and less and less likely. Now, we have, in a previous video, spoken about verifying that something definitely is a probability distribution. What I mean by that is it definitely true that all of these probabilities, in there infinitely many of them, do they all together add up to the number 1? Because they should do, otherwise this is not a valid probability distribution. So very quickly, let's just check this out, okay? How would we do this? Well, you guys might notice that this is actually, and a bit of a teaser in the name, this is a geometric series if I add them all up, right? All of them have 1 in 6, so 1 in 6. The next term is like 1 in 6 and then times 5 in 6. The next term is 1 in 6 times 5 in 6 times 5 in 6 again, and so on. So the first term, which normally you would call U1 or maybe A, some people like to call it A, is 1 in 6. The common ratio is 5 in 6. And if I do the sum to infinity, the sum of all infinitely many, you guys might know this is the formula for it. U1 over 1 minus R, or A over 1 minus R. In this question, it's 1 in 6 over 1 minus 5 in 6. And if I times the top and bottom of this fraction by 6, just to simplify it, I'll get 1 over 6 minus 5, which is 1 over 1, which is 1. That means that this does indeed surmount to a valid probability distribution, because all of these infinitely many values do add up to 1, which is pretty good. And that's kind of where it comes from, the name, the geometric distribution. So what exactly, because I've just given you one example, what exactly is a slightly more formal explanation or definition, you might say, of a geometric distribution? So a geometric distribution, which I'm about to fill in just a second, is one where the probability distribution follows a very, very similar pattern to the one that we did. The one that we've just done here, that absolutely is a geometrically distributed random variable, okay? And I'm going to explain what exactly that means in just a second. The most general form of a geometric distribution is one that looks like this. So I'm using the letter P here, okay? And P represents the probability of getting your success in any given attempt. So typically, in this question that we just did, that was 1 in 6. Because there was a 1 in 6 chance of actually getting the 5. In general, let's say that the probability is just P. So I've got P. That means I get my success instantly in my first go. The probability, definitionally, is just P. The probability that I get my success after I already fail is P times the probability of not getting P, so 1 minus P. The probability of it taking you 3 goes, you have to fail twice, and then you have to get your success. So you've got your success, and then you've got your 2 failures. So it's going to be written like this. And you guys can see the pattern. P times 1 minus P, that's cubed. P times 1 minus P, that's to the power of 4. And in general, guys, if I was to go, if I was to say that X is just some number K, let's just say K is some whole number, it doesn't really matter what it is. The part of the table that K is on, it would be P times 1 minus P to the power of K minus 1, okay? That's what that term would be, okay? That doesn't mean K divided by, that's part of the whole, it's inside the box, okay? And so that's the general form of it. And just to explain this, this means that after K attempts at whatever this is, the probability that you, for the first time, get your success, whatever that might be, maybe rolling the number 5, whatever the probability of it happening is, you've got 1 success and K minus 1 failures. That adds up to K trials or K attempts, right? And you have to fail K minus 1 times and succeed only once. That's why those powers look like what they are. So I'm going to replace this whole X represents blah, blah, blah with the most general thing from a geometric distribution. X represents the number of trials required to get the first success, okay? And when I say trials, I mean a trial could be something like rolling a die or tossing a coin, attempts at trying to get a success, okay? And the first success, and what I mean by success, is you actually get the thing that you wanted for the first time. So you land on the number 5, or maybe you're tossing a coin and it's the first time that you get heads, or maybe you're going into a goodie bag and you're trying to find, I don't know, a blue marble, and you replace the marble every attempt that you do. Okay, so lots and lots of different things have a geometric distribution. I'll give you another example. Maybe someone is trying to pass their driving test, and the probability that they pass their driving test in any given attempt is, let's say, 45%. Okay, what's the probability that they take 3 attempts to pass their driving test? That would follow what you call this geometric distribution. So when I'm talking about a distribution, I'm just talking about the way that the probabilities are spread out or distributed. And this geometric is a particular situation involving this pattern, okay, this structure of probability. So something that's geometrically distributed, and let's actually look at some notation. The fast way to say that x, the random variable, has this special distribution, geometric distribution, is to say that x, do a little squiggle, is geo, and then in brackets you put whatever p is. So in general it's just p, okay? This means x is geometrically distributed with parameter p, or you could say with probability of success p if you want. For the die question, we would have said that x is geo 1 in 6. That's how I would have written the die question that we just did earlier, okay? In general, we have the probability function, or the probability distribution function, that says this. For anything that's geometrically distributed, the probability that big X is equal to little x is equal to p times 1 minus p to the power of x minus 1, okay? And again, hopefully, even though it looks slightly complicated, it kind of makes sense, because again, all we're doing is we're saying, well, the probability that it takes lowercase x attempts before getting your first success is the probability of getting a success times the probability of getting all failures minus 1, okay? So you fail, you fail, you fail, you fail, you fail, x minus 1 times, and then on the x time, you get the success. This is what this probability is. That is what it is saying, okay? That is the idea behind the geometric distribution. So I think it might be a cool idea to actually go through another question and see exactly what it's saying, just to get a good feel for it. And in the next video, we'll look at some cool things like maybe the mean of a geometric distribution and stuff like that. Okay guys, so the probability that Sam passes his driving test is 3 out of 4. Assume that he makes 0 improvement between attempts. That means that even though he could be taking lots and lots and lots of driving tests, he doesn't make any improvement, he doesn't get any better, and his likelihood of passing doesn't change between driving test attempts. The question is to find the probability that it takes him exactly 3 attempts to pass. Now, you might not need to do all the fancy schmancy geometric distribution stuff to be able to answer this question, but I'm going to do it in order for you to get a feel for it, okay? Because other questions can be more complicated. So the first thing that we need to do is define a random variable. So we can say that x is the number of attempts for Sam to pass his driving test, okay? That's what x is representing, okay? And because of this, we can say that x has a geometric distribution, okay? That implies that x is geometrically distributed with a probability of 3 over 4, or a parameter of 3 over 4. This is how we write it. And remember, we know that if x is geometrically distributed with a probability p, the probability that x equals lowercase x is given by that formula there. So that means that we can say the probability that x is exactly 3 is just going to be 3 over 4 times 1 minus 3 over 4, which is 1 over 4, to the power of 2, because it's to the power of like 3 minus 1. Okay, and then we just work out what this is. So 3 over 4 times a quarter squared, that's a 16th. This ends up then being 3 over 64. So that's saying that there's a 3 out of 64 probability that it takes him exactly 3 attempts to pass his test, okay? That's how you use this. So in my opinion, it's actually not that complicated, but it's just a case of a lot of people struggle with like getting to grips with this stuff for the first time. So hopefully that makes sense. In the next video, as I said earlier, we'll look at, well, maybe not the next video, but we'll look at some point at the expected value of a variable, of a random variable that is geometrically distributed. We will look at the variance, and we'll also look at things like the probability that big X is less than or equal to little x, and things like that. So imagine that the question was something like, find the probability that it takes Sam less than 4 attempts to pass his test, or even the probability that it takes him 5 or more attempts to pass his test, and stuff like that. We'll look at mathematical algebraic expressions for all of this stuff, but we'll do that all in good time. For now, as an introduction to what the geometric distribution actually is, that's what I've got for you. So the takeaway of this video is the geometric distribution is a way to model and explain the number of trials or attempts that's required before getting your first success at one thing, where the probability of getting a success in any given attempt or trial is fixed. 3 over 4, 1 over 6, whatever it is, that's what the geometric distribution actually is. So guys, as always, I really appreciate you guys watching. Feel free to subscribe and like and share and all that good stuff if you enjoyed the video. Quick public service announcement: you'll never ever see a mid-roll ad on this YouTube channel. If you ever see one, leave a comment and I will come in, swoop in and delete it. I don't like the idea of having mid-roll ads on an educational maths channel, so I don't do them. Thank you so much for watching. As always, I highly appreciate it. You guys know that, and I'll see you in the next one. Cheers.